Hi everyone! Today we are going to do something different. We'll go through one interview question that I got asked during interview with the high frequency trading company, in short HFT. HFT companies are very heavy in C++, and more specifically they are very heavy on modern C++. It's very common for them to ask about template metaprogramming and some idioms such as SFINI, which stands for substitution failure is not an error. In that interview round, interviews were mostly looking to see how fluent candidates, such as myself, were in C++. With this being said, let's just jump into the code editor and I will present a question. Okay, now, and the question is, implement stud variant. Before we start implementing, let's have a look at what is the stud variant. If we go to the CPP reference and search for the stud variant, we'll see that the stud variant is the class template that represents a type safe union. At any given time, the instance of stud variant will hold the value of its alternative types, or in the case of error, no value. Let's go to the code editor and let's use it a little bit. I already included the variant header, so I will just starting to use it. As we saw in the CPP reference, it's a class template and it's accepting arguments as a template parameters. We will use the integer, we will use the string, and the size t. We'll call it var. Now we will use the string first. Let's say that we have a hello, then we will print it. In order to print it, we will need to use the get function template, and the string will be the first argument here because we start from 0, and we will pass the variable. This is the first output that we're going to expect here. And then let's repeat it for size t and integer. So the size t, we will instantiate it with the variable, with the value 1000, and the integer will be with the value, let's say 2000. And then here we are going to expect size t and then integer. Okay, now we're going to build it and print. Okay, we have an uncode exception of the bad variant access, and it's actually expected. The reason for that because I have a copy paste error here, and I always use the 1 as a template parameter. And in this case, it's wrong because the string is the first, the integer is the 0, and the size t is the second. So now let's change it to the expected values, rebuild it, and we execute the program. So as expected, we have a hello for string, for size t we have 1000, and for integer we have 2000. Okay, let's work on our custom variant. First of all, we know that's a class template and it accepts variadic number of types. So we will use the template and the type name with the 3 dots, which signifies the variadic number of types, and we call it types. Then we have a class which we will name variant, and inside that we will have a private methods and members. Let's think what to put in the private members. Based on the stud variant example, we need to know which type is currently active. So we need to know the index of the type in the past parameter pack, and we also need to store the largest type passed in the template arguments. So for that, in order to have an index, we will have a size t and we'll call it index. And we need to have a storage, which we will call storage variant storage, which also be the class template, and we call it storage. When the variant is default constructed, it is instantiated with the first type from the parameter pack. Let's work on the default constructor. But first of all, we need to know the type of the first type. We'll use template metaprogramming to extract the first type from a parameter pack of types. We define a primary template that has no definition and it accepts the variadic list of types. The primary template does not provide any implementation or specialization. So let's work on that here. We will have a template with the type name, as always, and then it accepts the variadic number of parameters, types. Then we will have a struct. In the struct, it's gonna be get, let's see, get first type, for example, get first type. Okay, now we will define the partial specialization. We will have a template with the type name, head, and head, it's the first time in the parameter pack. And then we have a tail, again, type name, 3 dots. We call tail. We'll have a struct, get first type. So we have a head, and we have a remaining types tail. We'll use the type as an alias for the head. Okay, let's go to our custom variant class and use the getFirstType to extract the first type from the parameter pack. We'll have a using firstType equal. Then we need to call getFirstType with the types. And then we need to have a type. However, let me remind the type to types. And then we need to use a type name here because the type is the dependent type that needs to be evaluated by the compiler. Okay, now we are ready to write a default constructor. In the member initializer list, because we know that the default constructor is using the first type, we can initialize the index to 0. Let's quickly write it. We have a variant, default constructor, and the index will be initialized to 0. Now, for the storage, we will pass 2 arguments. The first one is the type trait that represents the index of the first type in the parameter pack, which will be 0. And the second is just a call for the default constructor of the first type. So let's quickly implement that. We have we call it storage, so we will have a storage. Then, as we just mentioned, that we'll pass 2 parameters. The first parameter is the type, and it will be integral constant, and then the interval constant accepting 2 parameters. The first one is the type, which will be the size t in our case, and as I mentioned, it will be 0 because it's the first type from the parameter pack. And then we need to extract the getFirstType, but because we have an alias for that, we can just use the first type and call a default constructor. We just implemented the default constructor, which is actually the easiest one from all other constructors that can be implemented in the stud variant in our custom variant class. So as we just defined it, let's also work on a constructor from a given type, as an example here, or here and here. So it would look almost identical, but with it's going to be more complicated. And in order to define a constructor, we need to find the index of a given type in the parameter pack. In order to extract the index from the parameter pack, we need to define another class template that we'll call getIndexType. Let's work on that. We'll have a template, type name t, and the type name types. It's a struct getIndexType, and it's a primary template with no implementation. Now let's also define base case. Again, we have a template with a type name t and a type name types. But now it's gonna be a specialization of the getIndexType with the t, and the types. And here we have t and the types, and the reason for that is because in this specific case, why it's a base case? It's a base case because the first type is equal to the first type in the parameter pack. That's why it's a base case. And for the base case, we are gonna return the index which equal to the 0, and it's gonna be static const export size t value and the equal to the size 0. You can think of that as a recursion. When we recurse through the recursive call stack, when we meet the base case, sometimes we return 0. So that's basically how you can think of it. And the last thing that we need to work on is that we need to define a specialization when the type name t is not the first type in the parameter pack. So we need to recursively call the getIndexType in order to find the index of that type. Again, we have a template with the type name t, and then we have a type name head, and then we have a type name tail, which means that the type name t is not the same as the head. We have a struct. We have a struct getIndexType. It's gonna be t head and a types, or we call it tail here. Okay, yeah, let's call it tail. And now, again, we will have a static const export size t value, and then, okay, everything is good. So as in a recursive technique, we usually recursively call the function again and again. And for us, because of the problem definition, we need to find an index. So we will call the recursively getIndexType and add 1 here. So in this case, we'll just implement 1 plus getIndexType. Then we will have a t and then a tail. And then value. Okay, now we are ready to implement another constructor. Again, it's a variant, and we will have a value with the particular type. Then, because it's gonna be some time, we need to write a template, and we need to initialize the index first. So that is the reason why we wrote a getIndexType. So the getIndexType, the first will pass the type. The type is the type that we are searching in that parameter pack to get the index. So we'll pass type that we got from the constructor, and then we also pass the types that we get from the class that was instantiated with. and then we need to extract the value. We just get the value from that. And what for the storage, it's actually almost the identical that we have here. We will use the integral constant type traits, again with the size t. Now we need to have the index, and for that we just call the same thing. We call the get index type trait, we pass the type and the types, we get the value, then we instantiate it. It's going to be just a default constructor, and then we also now need to pass, actually we can forward that. We can call stud forward with the just with the type, and we will call a default constructor. So it's gonna be type and then value. Now it looks pretty much long, so we'll just use it like this. And we can actually pair it with the destructor. Destructor will be pretty simple. The only thing that we actually need to do is just to destroy the storage that we have for that type. So our storage member will have a, let's say we have a destroy method, which will just call, and then we'll pass our index. Okay, let's quickly finalize the implementation for the stud variant before we can jump into the variant storage, because the variant storage is actually the most important thing in that exercise. Okay, first we need to implement the get method. And the get method will accept the template parameter with the size t. So it's gonna be the template method with the size t as the type, and the name will be the index. The get, the name of the function, and we're gonna return wherever we store in the variant storage. So we call the get with the index. We need to use template here because the index is the dependent type. And the only thing that we also need to add here is that we need to return type. But we actually don't know what is the type, because that's going to be a return from the get of the variant storage. Luckily for us, we have the author, which gonna be deduced by the compiler. And the last thing that we need to implement here is the assignment operator, because of the example here and the way how we use it in this example. So for the assignment operator, it's also gonna accept the template. So now it's a template, and then we have a type name, as always, type. Now we already know we are gonna use the C++ auto in order to deduce to return type, and then we have an operator equal, that's gonna be our assignment operator, and then we have a type with the value. So now we need to have, and we need to know the index of that type in our parameter prac of the class. So we have a const expr size t index, and that index, in order to find the index, we already know how to do that. We just need to call the get index type. We pass the type, and then we pass the types, and then we call value. Now, first of all, the first thing that we need to do is we need to destroy the previous type. So we need to call variant storage, the destroy method, and then we already know the index because it's stored in our member, and we pass the index here. So now the memory is released for the previous type. Now we can assign the index of the other index, which is actually the index we just got from here. And we can call the get with the other index, and because we return the reference, we can just assign or move the value to using that reference, and then we need to return this. So here you can see we need the const explorer is because we need to call get of our method, and that our get is only work with the templates, which is compile time, and that's why we need to use the const explorer here. Okay, now we'll focus on the most interesting part in that problem, and this is going to be the variant storage. Let's implement it here. So, and then we work on a base case now, and then we'll move to the more general case. So for the base case is that we have a template with the type name, type, and then we have a union, we call it variant storage. And then in the base case, we just only have one type. This is going to be a specialization, and as I mentioned, we're going to work on a more general case just a little bit later. So for that, for the variant storage, we need to have, first of all, we need to store that. We need to store that type, so we call it type value. We have a value with the type, which is type. Now, we need, as an example below, we need to define the constructor, we need to define the get method, we need to have a destroy method. So we need to have three entities here. So for the first, which is going to be also type name like other, for example, we have a variant storage, and the variant storage, as we work on that before, it accepts two arguments. The first one is the type trait, which is the integral constant. It's going to be size t, and it's going to be 0. And it's 0 because in this case, this is already a specialization. So in this case, it's going to be just, we know that it's a first type, and the first type is at index 0. So, and then we have a value, so it's going to be other, we have a value, and then we just need to, let me implement it here. So we have our value, and then we have call forward with their type, other, and then value. And this is going to be our constructor. Again, we pass the integral constant size t0, and then we have a value, and we forward pass to the value. So that's basically it. It's pretty quick. Now, another thing that we need to have is that we have a size t index and our get method with the and our get method. So now the only thing that we need to do here is that we need to return the value, and the reason for that is because we know that our index has 0 and we couldn't traverse more, so that's our base case scenario, and we just need to return the value. And one more thing is that we had a destroy method for the value here. So, and for that, we just need to invoke a destructor for that particular type. And in order to do that, we just need to call destructor. So this is pretty simple thing here. We can even inline it and then just have in a one line, because that's a base case scenario. We don't need to do anything more than that here. Okay, now we need to work on a general case. We will have our union with the variant storage, and in this case we'll accept the first type as a type, and then the rest of the types we'll call it types. Now we will have a type for our type as a type, and then the rest we'll pass it to the variant storage types. Basically, we'll forward all other types to the next level of the variant storage. Now we should work on the constructors. And we will have multiple of those. So again, we'll need to work on the general case when we just have the only one type. And in this case, the constructor will accept the integral constant of size t with the index 0, and then we will have the other value, we'll call it val for now, and then we initialize the value with the, and we perfect forward the val here of other type, and then the val. So this is just a general case. Now when we should define another constructor, and in this case it will have the argument with the size t index, and again there will be another type. In this case we'll pass an index here, because we should basically pass the index that we got from the variant that we have, and then we have the value for the other. So the first thing that we need to do is that we need to call the constructor for the rest. So, and now we are passing the index -1 because it's the next level, and then we need to forward the value that we got here. So this is basically the constructor. Now we need another constructor. So for the another constructor, we will accept the size t index and the other type. Now we need to pass, instead of 0, we need to pass that index here. And then for these, because that's not the base level, we need to pass again the integral constant with the type size t and an index -1, because it should be the next level. And then we need to forward the value with type other. This is gonna be our two constructors here. Okay, let's work on the rest of the methods. So the first one is the gate. So it's a template with the index with the type of size t, and then we are gonna return the auto reference and then the get method. So in this case we need to use the const expr, because we need to know if the index is 0 or no. If the index is 0, we just need to return the value. Otherwise, else we need to return the get from the rest that we have here. So you can see it's basically the same syntax as we have down here. So you can see we're in storage dot template get index, but in this case we because it's not the 0, so it's not the element that we need, then we just need to return get in the rest, we call rest, and then the get index -1 from the rest. Another thing that we need to implement here is the destroy. And destroy method accepts just a runtime index, not the template. So, and then here we just need to compare it with 0, and if it's 0, we need to call the destructor of the value. Else, we need to call the rest.destroy and then index -1. This is it. The only thing that we can also add is the destructor here. We can have it default, or we can just leave it as the empty braces. So let's try to build this and see what we have. Okay, we have some multiple compilers and then unknown time of size, of course, because it's a size team. Then we have a template. Variant storage requires template argument. Oh, that actually makes sense because I need to call the storage, not the variant storage. I think that's the same thing. Okay, let's clear that and then build one more time and see if we can build it. Okay, we can build them. And now let's jump to the main function and then implement whatever we have here. So we'll have the same variant, but not from the standard library. So we'll just call variant var, and then let's see if we can just compile that. We can compile it. Now let's copy paste it from the original code. The only thing that the get method is a bit different, so we should just use the method of the variant. And then let's see if we can compile this. We can do that. It's perfect. Now let's do a similar thing for the other types with the size team and an integer. Here we'll have a variable get for the index 2 and then get for the index 0. Okay, so that's good that we don't have red highlights. Let's see if we can compile that. Okay, we have a compile error. Let's see what the compiler that we have. So it says that no member name story. Okay, of course, because it should be destroy. Let's try to compile it one more time, and we have other errors. It says that too many arguments for function call expected 0, but they have 1. Let's see. Of course. So we have here the index, which we actually not using. Okay, now we can compile that. So we can run it. And we have the same output as we had before. So the first thing that the string should be hello, then we should print 1000 of the size t and then 2000 for the integer. So we have similar output, the same as for the stud variant. Let's summarize what we learned and what we have here. So we use variant storage. The variant storage is the union, and we use the variadic templates. So we used union because we want to allocate just enough memory for the largest type. Next, we used integral constant. The integral constant is basically identifying which type at that moment is being constructed. We also use that recursively to forward other types to the next level of the variant storage. We also used here the perfect forwarding to preserve the value category of the value. And that's basically it. So that was the question that I got asked during the interview with the high frequency trading company. It was a nice experience. The interviewer was helpful, and sometimes when I got stuck, it directed me a bit for the right solution. But yeah, you can see here it's just like 100 line of code, and we implemented. We basically have a simple mimic of the stud variant. Of course, the stud variant is much more complex and has the different API. For example, here we just use the get of the variant, but the standard library has like a dedicated get, which just accepts the variant of multiple times, so it's a bit harder to implement. Yeah, so that's it for today. Thank you for watching and have a good day.